Well, it says draw the Lewis dot structures for aluminum, oxygen, lead, chlorine, and calcium. Well, how many dots do you put in the Lewis dot structure for a main group element?
It's based on your valence electron.
It's based on your valence electron. Good. So if you have your periodic table, find aluminum on your periodic table. What group's it in?
3.
It's in group 3A, so aluminum is just going to have 3 dots. It doesn't matter where you put them, here, 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 or here, 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 or here, here, here. It doesn't matter. They have nothing to do with molecular geometry, but this would be the Lewis dot structure for aluminum. What group is oxygen in?
6.
6, good. 1, 2, 3, 4, 5, 6. Okay, and usually we pair them on. It doesn't matter which sides you pair them. Okay, but you got 2, 2, 1, and 1. What about lead? What group is it in?
4.
Okay, 1, 2, 3, 4. What about chlorine? What group is it in?
7.
Okay, it's a halogen. 1, 2, 3, 4, 5, 6, 7. Doesn't matter which side you put the single electron on. Okay? Calcium, what group's it in? 2. It's in 2A, 1, 2. Okay? Nothing to it, right? Lewis dot structures are these elements. These are main group elements. We only use Lewis dot structures and the concept of valence electrons for the main group elements, 1A through 8A. We don't use them for the transition metal. Draw Lewis dot structures for oxide. Well, what does oxygen have to begin with? Okay, what is an oxygen atom? How many valence electrons did it have?
6.
6.
1, 2, 3, 4, 5, 6. What's the charge of oxide?
-2.
-2. So we need 2 more electrons. It has an octet. That's why it has a -2 charge. Because when it has a -2 charge, it has a full octet. Okay?
So you just draw it with 8?
Yep. And this, of course, has a 2- charge. I don't want to forget that. Okay? That's why oxygen, when it forms an anion, gains 2 electrons from somewhere, has a -2 charge, because it gives us an octet. How many valence electrons does sulfur have? Oh, I'm sorry, nitrogen. How many?
5.
5.
5, okay. So this is a nitrogen atom. And what's the charge does nitrogen have when it forms an anion?
-3.
-3, so we have to add 1, 2, 3 more electrons, and this is 3-. Again, it's an octet, isn't it?
Yes.
That's why it gets 3 electrons in the first place. What about, how many valence electrons does sulfur have?
6.
1, 2, 3, 4, 5, 6. Sulfide has a charge of 2-, it gains 2 more. Octet. These are all octets, aren't they? What about fluorine? How many valence electrons?
7.
7. Well, halogens like fluorine gain 1 electron and have a minus charge. There you go, it's just another octet. This is fluoride. You probably have it in your mouth if you brush your teeth. Has a negative charge, okay? Now hydride, it's a little different because hydrogen doesn't form an octet. How many valence electrons does hydrogen have?
1.
1. If it has a negative charge, it has 2. This is hydride. It has a -1 charge, okay? What is hydrogen? When a hydrogen has a -1 charge, and there are compounds that have hydrogen, like sodium hydride, lithium hydride. Its electron configuration when it has 2 electrons is just like the noble gas
Helium.
helium. But it's an exception to the octet rule, but it doesn't form an octet, it just gains one electron and has two. Like helium, right? Website. Okay, if the difference in electronegativity is zero, according to your textbook, it's covalent. In other words, non-polar covalent. If, according to your textbook, if the difference in electronegativity is greater than zero and less than 2, then it's polar. And then if it's greater or equal to 2, then it's ionic. So we use that as guidelines. And some of these, it's pretty straightforward, but first of all, let's do B. If you have a nitrogen bonded to nitrogen, well, they both have the same electronegativity. The difference in electronegativity is 0. So it's non-polar covalent. Okay. So going back here to the KBR, now you can, these are on opposite ends of the periodic table, so you can guess, but potassium 0.8, what was it? I forgot already. It's potassium bromide, KBR. 2.8 and 0.8. So the difference in electronegativity is 2. It's close. It's ionic. Okay, and you know that metal, non-metal typically are going to be ionic. When you have 2 non-metals like carbon monoxide, okay, difference in electronegativity between carbon and oxygen is 1. 3.5 minus 2.5 is 1, so it's going to be polar covalent, isn't it?
Are we gonna have that graph on the?
Yeah, if you need it, yeah. One thing, if it asks an obvious question, like which of the following has a non-polar covalent bond, if you see 2 atoms of the same element,
Then it would be
that's your answer. But definitely, if you need, whatever you need would be on the board. And then magnesium sulfide, we expect it, you got a metal and non-metal. We expect it to be ionic. Magnesium 1.3, and you can see that magnesium sulfide has, and the difference is 2.5 minus 1.3. So, according to your book, that has some covalent bond properties for an ionic compound. Anyway, you get the idea. Draw the Lewis dot structures for water, ammonia, methane, hydroxide ion, and hydronium. Okay, well, water, of course, you have oxygen, has 6 valence electrons, and you have 2 hydrogens that each have 1. So I'll just put a hydrogen here with its electron. I'll use an X for hydrogen's electron. And 1 here. Now the oxygen has an octet, doesn't it? The Lewis dot structure of a water molecule. This is why oxygen forms 2 covalent bonds, as it results in an octet in its valence shell. For ammonia is NH3. Nitrogen, you're going to need 3 hydrogens. Nitrogen has 1, 2, 3, 4, 5 valence electrons. You bring over a hydrogen, another hydrogen, and another hydrogen. And there's 1 lone pair, okay? Just for your information, there's 1 lone pair. That's ammonia. Methane, now you're going to need 4 hydrogens, aren't you? Because carbon forms 4 bonds. So carbon has 1, 2, 3, 4 valence electrons. Bring a hydrogen here, a hydrogen here, hydrogen here, and a hydrogen here. Again, I'm just drawing the hydrogen electron with X's so you can see where it came from. Now the carbon has an octet, okay? Now hydroxide ion is OH minus, there's a -1 charge. So it's going to have one more electron than the atoms have. You have an oxygen here with 1, 2, 3, 4, 5, 6 electrons. You bring over a hydrogen that has 1, but it has a negative charge. I'll make it a different color if you want. So this picks up an electron somewhere, and now it has this whole thing has a negative charge, and the oxygen has an octet. Okay? Hydronium ion. You're going to need 3 hydrogens for hydronium ion. And oxygen has 1, 2, 3, 4, 5, 6. And hydronium has a charge of +1. So it's going to lose 1 electron in this process here. You bring over 1 hydrogen here. Now you got a covalent bond. You bring over another hydrogen here. You got a covalent bond. If you bring over another hydrogen, now you have a problem because you have 3 electrons. But if you lose 1, now it'll have a plus charge. Okay? Lewis dot structure of hydronium. Okay? What? Assuming the octet rule is obeyed, how many covalent bonds will be formed in molecules for the following non-metal elements? And of course, well, there's one element on there that doesn't obey the octet rule at all, so, except you should know the answer to the question. How many covalent bonds does carbon typically form?
4.
4. It has 4 valence electrons. It wants 8, so it forms 4 bonds. How many bonds does oxygen form? 2. It has 6 valence electrons. It forms 2 covalent bonds to have 8. How many covalent bonds does fluorine form? 1. It's got 7 valence electrons. It forms 1 covalent bond to make it 8. How many does nitrogen form? 3. It has 5 valence electrons. It forms 3 covalent bonds to have 8. And then what can you tell me about helium? It's a noble gas and it doesn't form covalent bond. In a hydronium ion, let's draw the hydronium ion. Hydronium ion is an example of oxygen not behaving as in a typical way. Usually oxygen has 2 covalent bonds and 2 non-bonded pairs, but when you see hydronium ion, you immediately know that this oxygen might have a formal charge that's not equal to 0 because it's not behaving in a typical way. So you always can go ahead and calculate it. How many valence electrons does oxygen have from the periodic table?
6.
6. All right, so we got 6 minus, now how many non-bonding electrons? 2. Okay, minus 1/2, and how many bonding electrons?
3.
Don't forget, each covalent bond is 2 electrons.
6.
2, 4, 6. So it's half of 6, right? 6 minus 2 minus 3, and you predictably end up with +1. And so this is the reason this whole ion has a charge of +1, is because the oxygen has a formal charge of +1. The hydrogens are behaving, quote, normal. Okay? All right, well, we just saw it a few minutes ago. Can you name the 4 elements that can expand their octets in compounds?
Sulfur,
Sulfurs, phosphorus,
silicon,
silicon,
chlorine.
chlorine, okay? What compound, name 2 compounds, or what are the formulas of 2 compounds of nitrogen and oxygen that do not follow the octet rule?
Nitrogen oxide and
Nitrogen oxide's 1 and
nitrogen dioxide.
nitrogen dioxide, right on your study guide. Write a compound for beryllium and boron that doesn't have a complete octet, and there's examples on your study guide. Beryllium chloride, BeCl2, and boron trifluoride, BF3 are examples. Chapter 10, number 1, give the number of lone pairs around the central atom and the molecular geometry the following. And we already had, well, methane up here. Do you remember what its molecular geometry was?
Tetra.
Tetrahedron. And how many lone pairs did it have? 0. Okay. We had ammonia up here. What was its molecular geometry? Trigonal pyramidal. And how many lone pairs did it have of electrons? 1. Good. What was the structure of water? The molecular geometry? Bent. Good. And how many lone pairs did it have on the oxygen? 2. Good. Now ammonium is a polyatomic ion, and it actually doesn't have any lone pairs. Nitrogen usually forms 3 bonds, but in ammonium, one of the pairs of electrons, the lone pair of electrons in the nitrogen forms a covalent bond to a proton or hydrogen ion. And this whole thing has a +1 charge, and if you calculated it, this nitrogen has a formal charge equal to 1. And so this is ammonium. It's a polyatomic cation. And we'll take a look at it. What's its geometry?
Tetrahedral.
It's tetrahedral. So when this, if you have ammonia, the formal charge of the nitrogen is 0. You have a pair of electrons here. The molecule is actually trigonal pyramidal. But when that pair of electrons forms a covalent bond to a hydrogen, now the nitrogen has a formal charge of +1, and it's tetrahedral. Hydronium ion, well, water is bent, but if we have, well, I'm not going to do it this way, I'll do it this way, so it's easier to see. See here, here's a water molecule, and its geometry is bent, but if one of these pairs of electrons forms a covalent bond to a proton or hydrogen ion, now this whole thing has a +1 charge. This is hydronium, H3O+. The electronic geometry is still tetrahedral, but the geometry of the polyatomic cation is trigonal pyramidal. Okay? And it has just 1 lone pair now instead of 2 that water has. Alrighty, I'm moving on here. Here's here's an aspirin molecule, acetylsalicylic acid, and this problem's asking for each carbon in the molecule. And it's about 6 o'clock. Katie, did you want to go, or?
I'll just wait till you finish this and I'll go.
Okay. Again, if a carbon has 4 single bonds, it's sp3 hybridized. If it has a double bond and 2 single bonds, it's sp2 hybridized. And if it's got a triple bond and a single bond, is SP. Well, I don't see any triple bonds, do you? So this carbon here, right here, has 4 single bonds, so this is SP3. This carbon has a double bond and 2 single bonds, it's SP2. All the way around this ring, SP2, 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 SP2. In that molecule, there's only one carbon that's SP3 hybridized, and all the others are SP2 hybridized. Okay? Does everybody see that?
Yes.
You have to sit on that carbon and see what bonds it's formed. Like on this one with the carbonyl group here, that carbon has a double bond and 2 single bonds. That tells you it's sp2 hybridized, okay? Everybody see that? Now this is kind of busy. It's asking how many sigma bonds and pi bonds are in the molecule. Well, do you remember if you have a single bond, how many sigma bonds do you have?
Say again?
If there's a sigma bond, I just answered the question. If there's a single bond, there's 1 sigma bond. Okay? If there's a double bond, there's a sigma and a pi bond. If there's a triple bond, there's a sigma and 2 pi bonds. Well, there's no triple bonds, so we don't need to worry about that. And the number of pi bonds is easiest because each double bond you see here has 1 pi bond. So let's just count them. 1, 2, 3, 4, 5. In this molecule, there are 5 pi bonds.
And then the single bond is the.
And then the single bond and the other one from the double bond. In other words, for the sigma bonds, you got to count all the bonds. Because a double bond has both a pi bond and a sigma bond. So you got to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. There's 21 sigma bonds and 5 pi bonds. Does everybody see that? Now on this bond order thing, here we've got C2 diatomic carbon, oxygen, nitrogen, boron, and then we have a diatomic oxygen cation and a diatomic oxygen anion. And their bond orders will be different than diatomic molecular oxygen. For O2 plus, you got to take one of the electrons away from O2. For O2 minus, you got to add one. There you go. Thank you. They thought that was interesting, right? All right, so let's go here and cheat a little bit. Hey, I'm such a nice guy. Thank you again. I think I'm going to put this on the test. So if it asks you what's the bond order of C2, well, just look on the thing. But it's right here. It's 2. So for C2, diatomic carbon it's 2. For oxygen, diatomic oxygen, it's 2. It's a bond order. For nitrogen, diatomic nitrogen is 3. For borons on here, diatomic boron is 1. So all these are stable species that one way or another can be generated. Now in case of nitrogen oxygen, they exist at room temperature. Carbon, I think you have to heat it pretty high temperature, but you'll get closer to 2. Okay? So one way or another. Now what about O2 plus? Well, let's think about how we calculated these values in the first place. Does anybody see what's missing from these molecular orbitals? There's 2 molecular orbitals missing. And the reason is they're filled and we don't need to worry about them. Which ones are they? Well, you recall a 1s orbital and another 1s orbital give rise to a sigma 1s molecular orbital here and a sigma star antibonding 1s orbital here. And those aren't shown because they're filled. For these atoms, they're filled. You're gonna have 2 here, 2 here, the difference is 0, so it's not gonna affect the bond order that you calculate. So you don't even need to show them. Like for lithium, for example, there's 2 electrons in the 1s orbital, so there'll be 2 here and 2 here, it's filled. And so the only thing you see for lithium on this chart is the 3rd electron from each atom coming together, and they're right here. And this is the sigma bonding 2s molecular orbital. Everybody see that? Any question about that? Okay, so if these are, for all these elements here, if these are filled and we can just ignore them, because we'll get the same answer for the bond order equation if we include them or we don't. Because we'll have another 2 here and another 2 here, we can ignore them. So let's just use what's here and calculate what's the bond order for oxygen. Well, it's 1/2, how many bonding electrons, if you just consider the ones shown here?
5.
And there's 2 in a bonding order here, right? This is a sigma 2s bonding orbital here. There's 2 here, and then there's 2 here, okay? And there's 2 here, and there's 2 here. Wherever you don't see a star over here, those are bonding orbitals, here, here, and here. So you got, for oxygen, 2, 4, 6, 8. Now, how many antibonding orbitals? Well, wherever you see a star, these are antibonding orbitals. Don't forget, we're looking at oxygen right now. So there's 2 here.
4.
And another 2. Good. It's a total of 4. So, and you can see it wouldn't have mattered if we put the other 2 here and here. The difference would be the same. Does everyone see my point? There's no reason to have to show the 1s molecular orbitals at all when they're filled. Okay? So 1/2 of 4 is 2, and that's exactly what they have right here. Okay? So what about O2 plus? What's the difference between O2 plus and O2, the molecule?
It has an extra electron. I mean,
What's-
it doesn't have, it's
It's
missing an
missing one, good. Well, where's it gonna take it from? The highest. It's gonna lose one of these antibonding electrons, okay? And so instead of 8 minus 4,
electron.
it's gonna be 8 minus 3. Does everybody see that? And when this is gonna be 5/2 or 2.5. So for this species, the bond order is 2.5. And it does exist in a plasma. I mean, it doesn't. Okay. Now, let's go the other direction. What if we had O2 minus 1 charge? Well, where were we going to add our next electron? Again, up here we want to pair one of these now. We add one more electron now, and so instead of 4, we have 5. N minus 5 is 3/2 or 1/2. So for this anion, the bond order is 1.5. For oxygen, it was 2, and for O2 plus, it's 2.5. Does everybody see how we determine those bond orders?
Yes.
Okay.